Good morning, everybody. We don't have a lot of people in the class, but they're slowly trickling in. Welcome to this Wednesday, where we are starting a new chapter, our chapter on Babylonian numbers. Very exciting. All right. While we're waiting, can I get confirmation that everyone can see and hear me while we're waiting for people to come in?
I can see and hear you.
All right. So, what we have done so far is look at a different number system from history, the Roman number system, in a way that helps us with our goal. And our goal is to not fundamentally change what we're used to doing in arithmetic, but change things in appearance, change things just a little bit so that we are forcing ourselves to be aware of how our number system works, how our methods of arithmetic work, and just be very critical and really carefully think about it. Because if we do those things in our decimal number system, those things are so familiar, I immediately shut down my thinking and just go through the motions without realizing what I'm doing anymore because of the repetition I've been through my whole life. But as a teacher, potentially, I really need to be aware of every little thing so I can adapt my explanation, I can focus and elaborate on one step, I can guide the student more effectively. And that requires that I really understand what I'm doing first. So to help us, we have a couple of number systems that are very different, but both help us in that goal. We finished the Roman number system and we are moving on to the Babylonian number system. Now our goals will be the same. Uh, we are just looking at another number system, and we're looking at number systems that have a connection to our modern world today still. So we're not going to look at very strange number systems that have completely died out in terms of what we see today. We still have a connection to these. We saw in the with the Roman number system, it's fundamentally decimal, and we still have a connection to that, of course, because we count in tens as well. The Babylonian number system is going to look, I think, much different, but we still are connected to it. And I challenge you to think how as we continue. Now, to highlight the Babylonian number system, we have a little video. But before we start the little video, just explaining and sort of demonstrating because I'm not in class to physically show you. The Romans had connections with Egypt, and therefore they had a sort of a paper resource that they could write on. Great. So their number system reflected the writing options that they had. The Babylonians, however, did not have access to paper, so they couldn't write things down in ink in the same way. So they had to be a little bit more creative. How do they keep a record of quantities, of things, as they're trading, as they're assigning land, as people need to pay taxes, all these important things? What they did have a lot of access to is clay. So they decided to use this clay medium to represent their numbers. But of course, you can't write on clay as you could with ink and paper. So how do we represent numbers then? So I am going to play a little video. I just need to change my screen sharing option so that you can hear the video in Discord. Give me 1 second here. I not seeing it? Let me open it. Where are you? Okay, here it is. Okay. So let's see if that works. And if not, you can always watch the YouTube video after the fact if you maybe can't hear audio, but it should work. Okay, let's go.
Now all you need is a small piece of clay about the size of a golf ball or a table tennis ball, and to squash it out into a small disc. Here's our clay tablet ready to use. A small stylus, I've just cut mine from a piece of dowel, but in the old days I believe they used to use reeds, and then they used to cut timber much this shape. They used to draw lines, so I'll just draw some lines here quite a distance apart. They used to be a lot smaller, of course. And believe it or not, for all the sophistication of their number system, they used just two symbols. One of them was this one. Just poke a small mark into the clay. That would be the number 3, and they kept going. 4, 5, 6, 7, 8, 9. Easy. The next symbol they used was one like this, which represented 10, and they could make 30, 40, 50. The number I have represented there is in fact 59. If they wanted to represent the number 23, they do 1, 2, and 1, 2, 3.
Okay, 1 second while I switch the screen back here. Okay, now we're back. Okay, so move my microphone here. Okay. So now, of course, as much fun as it would be to play with clay and make these markings, we have to compromise and make these symbols that they would make in the clay by just drawing them on paper or the screen. So because of that, it'll seem a little clunky and inefficient perhaps, but remember, we're just representing the symbols. We're not doing it exactly the same way they would have done it. Babylonian number system. Okay, let me just check if my mic is working. I think everything's good. Okay, so because of their clay limitation, and they didn't want to swap out their dowel, their instrument, their stylus, that's a better word, they only had the option really to angle it in a couple of different ways. So to represent 1, they made a little indentation. There's a little flag-like symbol, right? You can try and copy the font I have here. Zoom in, zoom in, zoom in. This is the font that you'll see in the book, the only one I could find. Sort of trying to represent that indentation that you could get in the clay, just a little vertical line. Now I like to have my own style, but after a while it might look a little different. I recommend you try and make the symbol as you want, but don't just write a line like that, right? Be a little bit more creative so that we can see it's not the decimal digit 1. And then for 10, they would angle it sideways to make this little less than sign, like or a little eye, sort of, whatever you might see, or a little mouth, or whatever you can visualize that to be. They had to angle it in such a way that it's visibly a different uh, symbol that they're making, right? But if you have too many, then it's going to be hard to really make them obviously different, as people will have their own style as well, slightly different angles that people might have. You are kind of stuck in the sense that you can't allow many symbols because you need to make sure that regardless of who's making these indentations, if they know how to write, it'll still be recognizable. Just like handwriting, you still need to recognize the letters that the person writes, even though it might be a little different. So they decided, okay, we can get away with two symbols. And that's unfortunately it. Now we have to build a whole number system with two symbols so that our civilization can grow and develop and not die out. That is not a simple feat at all. What did they do? Well, for reasons that aren't completely known, they're only theories, they decided to uh, just start listing these numbers, just start stacking these symbols together. So let's write the first few. Oh, stupid line. So let's write the first few. And then as we do that, we can practice how we want to make these as well. So 1, 2, 3, 4, 5, 6, 7, 8. Of course, our first task is to convert, right? So let's say from decimal. So there I'll have my, oh, how do I write my little flaggy? How do I do it usually? My little flaggy guy. And then I could maybe write two of them. Sorry, a little longer perhaps. Just stack them. And then stack three of them. So as you practice these symbols, you'll find a compromise between it being recognizable and it being fairly fast to write. 4, I'm going to, let me just zoom in a little bit. I don't know why I put them so close together. They decided, well, it's going to be recognizable. I'm going to leave myself some space here. It's going to be more recognizable if I just put 3 in a horizontal row. And then I'm going to start stacking them underneath each other. And I'll put the fourth one, make it a little bigger so they seem connected. 5 would then be a row of 3 and then 2 underneath. 6, I didn't give myself enough space, so I'm staggering them. 6 would be a little smaller, but 2 rows of 3. And then I just keep going like that. But I'll have to have another row of 3 for 7. And for 8, see, mine look like little peas or little flaggies, and that's okay. For 8, I'll just start stacking them 3, 3, and 2. And 9, of course, will have 3 rows of 3. And the more rows I have, the smaller I'll make them. And then 10, whew, finally, I have a new symbol. Okay, whew, that's a relief. All right. So by doing this, we're practicing how do we want to make these little flaggies. That's mine end up looking like little flags or little peas, sort of pointy peas. As long as they are visibly different, these two symbols. And you only have two symbols to memorize. It can't be easier. Two symbols? Who can't remember two things? So then 11 would simply be a 10 symbol and a 1. Nice and close together because they are one connected representation, one quantity. 12 would be a 10 symbol and 2 ones, and so on. Nice and connected, like so. My flaggies get a little wobbly after a while. So let's skip forward and say, okay, what about 23? Then I would simply have uh, 2 10s, and I'm stacking them sort of diagonally, and 3 1s. Nice and tight, because it's one quantity. Let's skip forward, and let's say we have 40, let's go 7. So now I'm going to stack the 10s. I just want to be as authentic as possible, right? I'm going to stack my 10s diagonally until I get 3, and then, ooh, that was a curly one. Wow, look at that. It's nice. I like that, actually. I can do better than that. Let's be a little more clear here. My 10 symbols get a little curvy when it should be nice and sharp. Right, nice and sharp. Sharp. There we go. That's better. And then 7 will be a row of 3, another row of 3. See, I make them smaller so that the height is roughly the same. So it's now nice one connected thing, one quantity, but using repetitions of those two symbols. Okay. So I got a little excited, but we do actually have problems. Not problems. Why do I keep saying problems? We have no problems. This is fun. There's no problems here. We have exercises. Yeah. Let's look at an exercise. First kind of conversion in exercise 6.1 is, of course, given a Babylonian number, what is the corresponding decimal number? So let me just number this. Exercise 6.1, number 1A. I'm not going to copy it. We can just look at it. That is 2 10s, so 23. 23. Nothing more to do. You just have to understand how the system works. And in the first step towards understanding, it's as simple as just adding up all these pieces. They're just repeated to form the quantity. What is the second quantity? Well, now I have 4 10s, so 40. That's 47. That's exactly the one I chose. Wow. That's not very original. I'm sorry. Who made these examples? Silly. Now, this is the font that the book is going to use. So they stack them like this. It's the only font I could find. Lay them out however you want, as long as they are nice and tight together when it's one quantity. So here I have 39. 39. So they decided that, look, if I have too many of these one symbols together, it's going to start blurring together, and I can't quite tell them apart to see how many there are just by looking at it quickly. 9, if I stack them 3 by 3, okay, I think I can handle 9. But any more, so let's get a new symbol for 10 and then use that so that we don't repeat the same symbol too many times. Too many times. Okay. So they said, okay, 9 of these little ones and we're going to be okay. And the 10s are a different symbol, so we don't have an issue right now. All right. Then, of course, we want to convert the other direction. And here in the example, we have 22 to convert. Well, that will be 2. Oh, my 10s really are not good today. Let's make them nice and angled. Angled. If I want to write them, I can write them in a row. What was the other one? 22? Yeah. and then nice and tight, 2 ones. It doesn't have to be perfect. I, of course, made this look sloppy on purpose. Usually my writing is perfect, just to show you that it doesn't have to be perfect. You just have to keep them tight and make the two symbols recognizable. That is my requirement. We don't have actual clay. If you had clay, it's actually very easy to do. It doesn't feel easy, perhaps, when you write it. It feels clumsy and you have to draw pictures and it doesn't work. You have to figure out how to draw this. But in clay, it's very efficient. You make indentations and you just go like the video showed. But sadly, one downside of having a virtual classroom, it's not as efficient uh, to work with clay. But we do the best we can to try and imagine that it was, in fact, very efficient. There's a picture there. The guy just, from the video, actually, I stole it. Let me zoom out. Where's my exercise continued? Oh, over here. So before we get to the rest of the exercise questions, you see here they listed some representations of the first 20 and just sort of a cluster of these symbols repeated. So 30 will just be 3 tens, nice and tight together. So there's no question that this should go together. Whether you want to stack them like that or you want to stack them like that, doesn't matter to me. I think historically speaking, the second one is more correct or more authentic rather. They're both correct, but it's totally up to you as long as they are clearly together. And lastly, we have 48. So we want to have, oopsie, I don't want mine to look too much like a 4 sometimes. 48. So I have a row of 3, another row of 3 will be 6, and then 2 more. Nice and connected. See? Cluster of one quantity. Okay. How do we feel about that so far? Try and keep in mind that if they had the option of drawing on paper, they wouldn't have done this. Of course not. But given their situation, they decided to rise above it, figure out what would still be efficient, and they went with it. And they were very successful, very, very successful in this number system. And the key to a growing civilization, especially at that point, and really in general, is effective communication, whether it is language, whether it's numbers, it has to be effective in use and maybe in writing so that you can grow and share knowledge and convey information effectively. And that is exactly what they did. Any thoughts at this stage?
It sounds pretty cool. Does it go into like the hundreds and different
Yeah,
symbols
see,
like
so
that,
now
or?
now our issue is okay. So if you notice, our numbers have been fairly small, and for good reason. I just want to get into how this works. But they had to make a decision. Obviously, I can't stack too many of these. I limited myself to only 9 of these ones symbols. Okay, so let's say here, limit ourselves. They decided, look, if I have too many of these symbols in a cluster, I'm going to start losing my efficiency. I'm going to start having to look really carefully at how many of these one symbols there are, and it's going to slow me down, and I can't read what I need to read, and it's a whole bunch of problems. So they decided, okay, we're just going to have not up to 9 of the one symbol. Too many, and it's going to break down. So let's draw 9 of them. To help us, sure, we stack them like this. It helps. but anymore, and even the stacking is not going to help me anymore. Okay, nice and close together, fair enough. Anymore, they thought, it's going to be too bad. Okay, so we stop at 9. Okay, but we can have some 10s to make the quantity bigger. But they decided, well, based on the symbol, we don't want this cluster, this representation to be too big in either direction. So really, when we make a cluster of 10s, we can stack them. That's pretty much as far as I want to go. So they decided, I didn't decide it, they decided up to 5 of these 10s symbols. Maybe trial and error, slowly over time, they realized that, okay, this is as far as we're going to go so that we can still see very quickly the quantity and read it and move on with our lives. Anything more, and it slows us down and we really have to stop and count, and that's not how you want to look at a number and know what it is and move on. So that's as far as we are going to go. So this is equivalent to 59, right? But of course, I could be a farmer and have more than 59 chickens, and I need to pay taxes and keep record of my chickens and whatever else I need to do. So obviously I need to be able to represent larger quantities. What they decided is we are going to count in groups of 60. So now if I add one more here, if I have one more, now I have 60. How do I represent that? Well, if I have a larger quantity, like for example, let's say I have 64. The actual 60, we're going to have to wait on that a little bit. I'm going to just write it in my language first. I'm going to say that is one group of 60 and another 4 left over. So now I'm going to have 2 places in my number system separated with a clear space. I'm going to have one group of 60 space and then 4 ones. A clear space will indicate that this is a 2-place number. It has 2 places. The left place, the first, if you read left to right, is going to indicate how many groups of 60. Groups of 60. And the second place, the next place down the line, is going to represent how many leftovers, oops, or ones, or whatever you want to call it, how many is left over. So one group of 60 and 4 more in addition to that gives me 64. So in that way, by having multiple places, I can recycle existing symbols. Now, I mean, this isn't that foreign, really, when you think about it. That's exactly what we're doing in our decimal system. Except we say, let's say 24, and I'm going to write it in words so it looks a little strange. 24 is 2 groups of 10 plus another 4. It doesn't matter how I have represented it here. I could represent it in words. I could have symbols. I could make my own symbols and say, this is how I'm counting. Our decimal system is going to make groups of 10. They decided, we like 60. Why exactly? No one really knows. There are some theories that in terms of surrounding numbers, 60 has the most ways of breaking it up into smaller factors. The other numbers around it of that size doesn't work as nicely as 60 does. But still, we don't really know. And it's interesting. I think it speaks to the culture, the way of thinking at that time. Uh, a lot of it can be sort of concluded or gained from looking at how did they do things? What did they feel is a natural way to move forward, like with numbers? 60. What does that say about the culture of that time? I don't really know, but it's interesting. Regardless of the reasoning, they said, we are going to go with 60s because we're happy with representing quantities up to 60, up to not including 60. Below 60, we're happy with making clusters really one place. This is one place, a one place number. We're happy with making little clusters like that. With our clay, super efficient. We have no problem. So they didn't have the need, like we perhaps did, to stop at 10 and make more places. I see now there's a place for the number of tens, 2. There's a place for the number of ones, if you will, units, leftovers, whatever. And we write this in 2 places because we are basing it on 10. They were fine going bigger because their symbols allowed that and still had that readability to it. But too much, we're running into trouble. Let's cap it at 60. Okay. But in terms of a place value system, it's really not that foreign once you think about it. Place value system. So let's look at some exercises. And the next one is exercise 6.2. Let me zoom in. Now, I don't want to go too fast here. We've got lots of time. We have tomorrow as well. So we definitely have the time to just ease into it. Ease into it. But the place value concept is a key concept of this number system. So we have, of course, the task of how am I going to draw the symbols? Get used to that, making your little clusters. Do that first. Then worry about, okay, well, now I have to think of multiple places of clusters as well. But one thing at a time. Number one. Number one, A. So now I see I have 2 places. The space should be super clear. There is, of course, maybe a little gap there in my font, but obviously, it should be obvious that the 3 tens and the 5 ones make one place, one cluster. And there's a clear space, and then this 1 is a new place. I have 2 places. That means from left to right. I'm counting. Let me write this out. I have time. Why not? I'm going to write, let's do it like this. Number of 60s. And then number of, let's say it like that. Okay. So in the 60s place, I got 1. Let me maybe write it like, I'm not done. I'm just trying to figure out crossing over to my complete conversion. So make the brackets remind me, I'm not done. I'm just seeing what there is in that place. Okay. Then in my next place, the ones place, I have 35. 35. So that then means I have one group of 60 plus 35 left over. So therefore I have 95. So this 1A Babylonian representation is the representation for 95. So maybe something like this with lines reminding me what the places are doing, uh, with numbers in brackets because I'm not quite done. Maybe that helps me. Use it. Help yourself. especially if you happen to make a mistake. Like in the heat of the moment, I'm rushing because it's a test or whatever reason, I'm not paying attention, and I accidentally write 94. Having something else there to show that I do understand how to do this. I showed my work, I show understanding. I just happen to make a little mistake. That's always a good idea to have that backup to get part marks if that is available. If you just write 94 with nothing else, then it's a 0 because I don't know if it was a silly mistake or you actually didn't have any idea how to do this. So showing some work is nice. But of course, you can figure out exactly what you want to show and how you want to show it. This is an option. Okay. Next up in B, again, 2 places. I'm going to set this up. And hopefully in the first quiz, you saw that there was more than enough time, I think. If I'm well prepared, the time should not be an issue. So I set it up. 2 places, so I'm counting 60s and then ones from left to right. Let's see how many groups of 60 there are. There are 3. And then for the ones position, the ones place, there are 41. 41. And of course, you have to get to a point where you can very quickly recognize there are only 2 symbols. This is really not that difficult. So I'm setting myself up, and now I'm ready to say, okay, it's 3 groups of 60 plus another 41. So that would be what? 180 plus 41, 221. So this Babylonian number corresponds to what we would call 221, 221. And again, find a way that helps you get to that answer with confidence and show some work in the process. It's win-win. It helps you, it helps me, it helps everybody. But of course, it's day 1 in Babylonian times, so it might take a while. I'm only going to do this exercise, and it might be a good place to stop. We're not in a hurry at all. We have tomorrow as well. And then we'll start arithmetic. One thing at a time. Let's build up slowly and correctly. Okay, so we have a 2-place number. All right, so I'm going to help myself. I'm going to set it up. If you think that is silly, that is totally fine. And if you have the number correct, it'll show. Oh, sorry, I'm multitasking here. Multitasking is not my strength. Let me just finish what I was trying to write here. You can't anyway write just 221. At the front in the instructions of the test, it says show sufficient work to justify your answer. So if you want all the marks, you're going to have to show something. But exactly what that is, it's up to you. Okay, so we have 10 in the first place. So 10. Then we have 50. So 50. Of course, I'm not done. I've just sort of translated each individual place. I have to put it together in that system for how it works. So I have 10 groups of 60 plus 50 left over. That's, of course, 650. Okay. How do we feel about this direction for the conversion? Of course, it takes time. You may need time to review. Just slow down and think about it, and that's where the videos are very useful, or do whatever you need to do. Okay? It takes time. Don't be worried about time. We have the time. It's okay. No, I don't think I have enough space there. Let us see the other direction for the conversion. All right, so now we're doing number 2. First one, I'll write it down. 100. 100. Okay. Now I know how the Babylonian system works. It's counting in groups of 60. And I have a number that is bigger than 60. That means I need to split it up. And in this case, I have one group of 60 plus 40. So I need to do this breaking up of the number according to groups of 60. That will then mean I'm going to have a two-place Babylonian number. The left place is going to count the number of 60s. That was supposed to be an S. 60s. The next place is going to count the number of ones. I have one group of 60, 40 ones. Maybe I want to help myself like this. Sort of that transition to Babylonian places, but I'm not going to worry about the symbols just yet. Now I'll do the symbols. A 1, nice space, and then 40 stacked however you want to stack it. I'll stack it like that. At least get some curviness into that line there. Not my best 10 symbol, I know. Nice clear space in between. All right. So this direction has maybe a little more to it, that I have to take that decimal quantity, 324, and I have to break it up and say, well, how many 60s can go in here? Into 324, I can fit 5 groups of 60 in. That uses 300. And I don't have enough for another one, right? I have 24 left over. But I need to do this breakdown correctly, of course. Then I can go and say, okay, I have two places for the Babylonian system. First one is the number of 60s, and then the number of ones or leftovers or whatever you want to call it. Many people call it units, but that never sounded right to me. So I'll have 5 groups of 60, and I'll have 24 left over. That means I need two places. I need to represent 5 stacked however I stack it. I like this stacking. Nice space. 24. Oops. Technically, if it's not 3 in a row, it's a
I have
little
a question.
bigger. But whatever. You see the cloud. Yeah.
Why are you using the tens there instead of the ones?
No, you're right. You're right.
Okay.
My bad.
Thank you.
There we go. Of course, I mean,
Thank you.
of course, I did this on purpose, just to
Yeah,
see
just to make sure we're paying
who's
attention.
paying attention. And you passed. You paid attention. See? You passed
Okay,
the test.
that makes sense. Thank you.
Yeah, I don't know what I was thinking there. Let's go with I did it on purpose. So, and in fact, I mean, I'd say this middle step helps me look back and say, okay, did I do this right? Okay, this was supposed to be whatever this in this place. I just convert to 5. Oh, did I do that right? No, I didn't. Okay, let's go fix it. But I have this helping step that might help me catch a mistake, like I have demonstrated here. But you, of course, don't have to write a middle step. Just show the breakdown in terms of 60s and then go to Babylonian, or however many in between steps you need to help you get there with confidence and have a little safety built in, like we spotted it. By having that extra step, I spotted, with some help, the fact that, oh, I didn't represent 5, I represented 50. And that helped me realize that before it was too late. Now, of course, if the number is a little bigger, then figuring out how many 60s can go in there can be a little tricky. You can totally do it in your head, trial and error, do whatever you want to do, but we can also just do a division, because how many times 60 can fit into a number that is exactly the intuitive understanding of division. So let's see what MathBot says if we do 1337 divided by 60. 7 divided by 60. Hopefully MathBot is awake. MathBot says it is 22 and a little bit more, but not enough for another whole group of 60. So 22 groups of 60 will fit into 1337. Then I might want to know, okay, well, how much of that number have I used when I look at the 60s? So 22 times 60, and I see that I've used 1320. So obviously then there are 17 left. Now, maybe I'm not 100% confident here. I can then go and triple check and say, okay, let's see what this calculation is, and is it 1337? So 22, oops, I need two equal signs. 22 times 60 plus 17. Did I do that right? Yes, I do get my original number. Okay, now I'm doubly sure. But definitely this direction for the conversion is more difficult in that I have to figure out this breakdown of the number by way of 60. Once I have that, regardless of how, you can go and say, okay, I like the safety step. It helped me catch my previous mistake. So I'm going to keep doing that. It's not as if it takes very long. I am going to have 22 groups of 60 and 17 left. Now I just have to convert 22. That'll be 2 10s and 2 1s, nice and tight. Big space. Well, not too big, but big enough to be recognizable. And then 17. 17 has a couple of rows of 1s here, like so. I don't love this line here. It's a little straight. Make it nice and curvy. Something like that. Clear space, clear clusters. I double check. 22, yes. 17, yes. I'm good to go. Okay. So write enough, especially in the beginning. Show enough to yourself. Don't think just about the test. Help yourself. And what helps me is to see my thinking, so that if I get distracted by a bird outside, oh, okay, I'm back. Oh, right, this is what I was doing because I see it on the page. People think they want to write as little as possible because it impresses, I don't know who, someone. I can't think of who. Help yourself, write more. When in doubt, write more so that you can see and everyone can see what your thinking is. It's just better for everyone. Okay. So this is a good place to stop. More than enough things to practice. Of course, the story isn't finished, but we have tomorrow in the schedule, so why not use it? Plus, we're out of time anyway. Any last thoughts before we pause it here and pick it up tomorrow again? I know, there's stunned silence. That's okay. Until tomorrow. Good morning, everybody, to this Wednesday. I have to remind myself what day it is, where we are continuing getting some properties ready to find derivatives of more and more complicated functions. As always, just so I know I'm not just talking to myself, can someone just confirm that they can both see and hear me, and we will get going. All right. Now, it is worth reviewing yet again the properties that we have so far. If this is annoying you, good. That's exactly my goal. It should be repeated so much that it is annoyingly obvious and you know it so well. So, we have the power rule that says that if I want to find the derivative of x to the power of something, then I can put that exponent in front and the new power of x is 1 less. All right. But in order to get to the power rule, I need to have some other properties to actually get me to that isolation of x to the power of something. For that, I have, in no particular order, constant times a function. So by the end, I would have written these down many, many times. So I guess they're important. Maybe I'm just trying to keep myself busy. Everything I'm saying is important, and you should be able to make this list as well. If I have a number times the essence of the function, whatever that might be, something that involves the x's, that a cannot be an x, right? Then I can do exactly what I want to do, and that is leave the number out in front, focus on the derivative of the essence of the function, and move on with your life. So these properties are ones that I take for granted very easily because they say things the way I want them to be. And I almost don't even think that this should be verified by way of the limit definition. We can't just make it up because we want it to be like this. Next, we have the sum or difference property. Don't know why the power rule is called a rule, but the others are called properties. Whew, that was ugly writing. I can do better, I apologize. Okay, well, I can't do better, but I'm going to try. And the more I try, the more weird it looks. That says that if I have to find the derivative of, a function, but it's made up of multiple terms, maybe an f and a g. I can look at the derivative of each one separately and put them together in the way the terms were put together originally. It's pretty much exactly, best case scenario, this is exactly what I would want. To the point where it feels almost made up. Like, how can things be so perfect? Lastly, I have what I'll call the constant property. These guys don't really have names. I'm sorry. Why don't you have a name? Why can't I write better? Wow. There's no answer to any of that. I don't know why they don't have names, and I don't know why I can't write better. If I have a constant function, I know that's horizontal. Slope of horizontal line, 0. Okay. So all these are the ones we have so far. And we've practiced and practiced a good number. And if you need more practice, I assume that you do that. And if you need to go back and review, there's a prerequisite little gap in your knowledge. You need to go and fill those gaps. They're not going to fill themselves. But I'm happy to discuss that with you if you're not sure. You're something feels off and you don't know what. we can figure it out. But this derivative concept, an idea, and the big picture of what we're doing needs to be very, very solid if you want a smooth ride for the rest of the course, really. Calculus is all about this derivative. In different forms, but it doesn't really change. We'll see. Okay, so I want to make more complicated functions. Now, I can, I am limited to the essential fundamental type of function. I'm sort of stuck with powers of x for now, and that's okay. That's okay. But within that, I at least want to handle anything that's possible. Now, I have some basics like a number in front, a constant function, and I can add and subtract functions and still find the derivative. Then the next one would make sense to ask, well, what if I have, I'm going to leave a space here, what if I have to find the derivative of a function that has pieces multiplied together? Certainly that is going to come up a whole bunch. Uh, so we want to know, how do I handle a product? Now, for some reason, this is called the rule again. I don't know why. It's still a property. The question is, what do I do with that? For example, now there are problems, but I'm just going to make a random example. If I have y equals, what should we say? 2, let's say x apparently, x squared plus 1 times 3x minus 7. That's a function that could come up. And I see I have these brackets multiplied together. Now I certainly have the option. Let's call it option 1. Quite often to first simplify and multiply these things out to see what I have. First one's 3x cubed. Maybe then you FOIL according to FOIL. Outside ones, negative 7x squared. Inside ones, 3x. Last ones, minus 7. Totally good option because foiling is so easy, right? You've done so much of it. It can't go wrong. So it's reliable. And then I can go and say, ooh, let's mix it up. Let's go little d notation. Yeah. We don't see this guy enough. It'll come later. But this is just another name for the derivative, right? And I can quickly do my properties that I have so far. Some difference property is going to happen first. Then that's going to allow me to isolate each term. Within that term, I know that the constant times a function keeps the 3 in front. Then eventually I'll be able to use the power rule. That exponent's going to come in front as well and multiply with the 3 to give me a 9. The new power of x is going to be 1 less. And as I slowly do the detail and get used to it, I'll be able to very quickly find the derivative. But let that happen naturally by doing the detailed versions enough times for you. I've seen people, they go to quickly get the answer. They skip all the detail, right? Just find the derivative. When they're not really ready for it. I can't say when you're ready. You'll know when you're ready. And that is when writing out those detailed steps and explaining the property you're using on every line, when that gets so annoying and so obvious, then maybe you're ready. And if the question doesn't specify, it just says find the derivative, you can do it in one line if you're ready. Okay. So that certainly is option 1, sure. But it's not gonna take much for me to imagine that if I have more terms in the bracket, or those terms inside each bracket is messy and difficult, or I have multiple brackets, then multiplying these out could actually be quite time consuming. And I could actually make a mistake on the way. This one was fairly easy. Two terms each. Each part isn't complicated. It was manageable. But if this gets worse in terms of what the brackets look like and how many there are, yes, this option might take me a while and might not be the most efficient. Is there another option? Now let me make it clear. Yes, there is. I would have to be sure where this comes from, I would have to go. Now, I'm not going to do the whole thing because we don't need to. It's a little of it sidetracks us a little bit. I'd have to go and say, set up the limit definition on this function. So it'll be the function at x plus h, which will be x plus h g of x plus h, minus that whole function at x, and figure out what that is. There's some trickery involved that can help me figure that out in general, but that is what has to be done to establish a new property. There is no way around it. And I might want this property to be similar to the sum difference property. Saying, well, if I look at the sum difference property, well, I had two pieces added and subtracted. I just separate them and then put them together in the same way. So why wouldn't I be able to do the same thing here? Of course, I would want it to work like this, but I have a question mark still. I'm not sure. Let's have a look at this example and see. I know what the answer is. This answer is correct. This answer is correct. Actually, I forgot to do something. Oh no, never mind. Never mind. This answer is correct. Let's see what I get if we try and find the derivative by looking at the derivative of the first bracket times the derivative of the second bracket, right? Certainly, if I look at the sum difference property, it's as easy and straightforward as I could have hoped. It would be super nice if this product rule is also as straightforward and simple as I would hope it to be. Looking at each of the factors and their derivatives and then put it together in the same way. So that would require this line, okay? Again, I'm just trying it. So the first derivative is 2x, of course. The next derivative is 3, and that would give me an answer of 6x. And you see, I'm not even close. This isn't even close to the same. It was the same original function. Answers, nah, not correct. Unfortunately, whether I see the proof and understand the proof or not, this is unfortunately not how I handle the product of two functions. This is not complete garbage, but doesn't work like this, unfortunately. It's a little more complicated. Only a little, not a lot. So what is it? I'm going to write it in a version that you might see in the book. It's a little nicer to look at it this way, I think, with prime notation. It is the derivative of the first times the second plus the first times the derivative of the second. Not because I want it to be, I don't want it to be, but because it is. when you go through the mess of this general limit definition on this kind of function, and I'm happy to show it to you, it's just sidetracking us. It's not the focus of what we want to do right now. It's a little more difficult for sure. If you go through the motions, what comes out of that is what it is. And this is what it is. Now, there's some symmetry and nice aspects to this, making it a little bit easier to remember. It's not that bad, but it certainly isn't ideal. But it is what it is. What I feel is irrelevant. I want it to be simpler. Well, it's not. Suck it up. It's also not that bad. Just say it over and over to yourself, and it gets easier. Now think of it as I have a first factor and I have a second factor. First multiplied by second. The derivative of that is the derivative of the first times the second, then flipped around, plus the first times the derivative of the second. So it's not that bad. It's not that bad to memorize. But even if I see the proof, it's not going to help me memorize it. I just have to remember. Say it over and over. Derivative of the first times the second, plus the first times derivative of the second. Okay. How do we feel about that? Recognizing that how we feel is completely irrelevant because the proof is what it is. Sorry, I tried to unmute you, but you still have background noise. How I feel about it is irrelevant. It is what it is. Okay. Now the question is only, let's practice and use it. Using it is important. So now, this was all bad news. Bad. What is the correct version of option 2, the product rule? So let me rewrite this. I don't remember what I wrote. X squared plus 1, right? Yeah. X squared plus 1. No. What am I doing? Back it up. I'm just trying to rewrite the function here. Whoa, random line. 3x minus 7. Okay, that's that the same function. Why am I paranoid now? My skills of copying stuff down are lacking, to say the least. Okay, so now I see. Okay, it's the product of two things. That is how my original function is made. I can break it up into pieces, but those pieces are multiplied together. That means product rule. So I have, following the product rule, the derivative of the first times the second plus the first times the derivative of the second. Now see here how quickly we are leveling up and how quickly we are leaving the limit definition behind. Those are things you have to do. You have to understand ultimately what we are doing when we talk about the derivative. What are we talking about? What is the limit definition? Where does it come from? What is happening at that bottom level of detail and messiness? But for now, we are trying to establish all the things that we need to get out of that bottom level. Still finding the derivative, but in a more clean, efficient way. That means I need to look at different ways that the function could be made of smaller pieces. Added together, subtracted, constant piece, number times a piece, or pieces multiplied together. Those all need to be established if I want to step away with confidence away from the limit definition. So this is now practicing how to handle a function that is the product of two smaller, simpler pieces. Now I've now taken the original derivative and rewrote it to a longer thing, but the derivatives that I now have to find, these two, are much easier. And now I'm back to my basic properties because the first derivative here requires a sum property. And then I have a power rule. And then I have a constant property. So it's 2x. The 3x minus 7 comes down, waiting for me to resolve the derivatives that I still have. The x squared plus 1 waits for me to do what I need to do, which is find the derivative of 3x minus 7. In finding the derivative of 3x minus 7, so that's this one here, and that's this one there, that's next. Can we list collectively? There are 7 of us, excluding me. In finding that derivative of 3x minus 7, can we list all the properties that goes into finding that derivative? You don't have to list all of them. Just start saying properties that go into finding this derivative of 3x minus 7. Can you see the properties that are being used? Just list them. It doesn't even matter which order. For now, I just want to see. Can we see all the properties? Definitely constant times a function. Constant times a function. Definitely power rule, because there's an x to the power of 1, right? Okay. Any other properties that go into this? Actually, a lot more than you might think. Constant property, because the 7. Absolutely. Constant property. We've missed the first one that gets us to any of these. We overlook them. And my theory is that by overlooking them, we run into silly mistakes later when things get complicated. And we're heading towards that. There's one more property, arguably the most important one, because it comes first. I can't look at 3x. It's not isolated yet. I can't look at 7. I need, well, technically the difference property, but if you say some difference, totally fine. Because it's a minus in this case, difference property. Or you can always say some difference, that's also fine. All of them in combination allows me to say 3. But of course, I've done a ton of these. It's super easy for me. I need to make sure, and you need to make sure for yourself, that it's super obvious why it's 3 and nothing else. And if it's not, go back, rewatch videos, practice more, do whatever needs to be done. But my best advice, as annoying as I sound, saying the same things over and over and over, in the off chance that someone is hearing this for the first time, you have to build on a solid foundation. Or in a month from now, it's all going to fall apart. And it's going to be so hard to build up again. Build it as it comes up, layer by layer, and make sure it's solid. You decide for yourself whether this 3 is super obvious, because it needs to be. We're now heading into more complicated properties that help us rewrite to simpler derivatives that use my original 4 basic properties. So now it's just a matter of, I can totally leave it like this, but I want to simplify because I want to match it with my answer up here to see if they're actually the same. So I have an extra objective, and to see if I get the 9x squared minus 14x plus 3, which I hope I get. So let's see here. I have a 6x squared, multiplying the 2x in, then a minus 14x. Multiplying the 3 in, I get a 3x squared and a 3. I'm going to zoom out because I don't like scrolling up and down so much. And hopefully everyone's convinced that we get the same answer. So as not obvious as it may be, why the product rule splits these pieces into multiple terms, it's necessary to get the answer that I need to get. There's only one right answer here. The derivative of a function is a specific other function. Regardless of which route I take, it needs to get me to the same answer. Okay. So we have the product rule. Now, because I know some people are, it takes a while. They're a little shaky. It takes a while to get on top of all this, to understand the big picture, to understand the different properties, what we're trying to do, what we're saying, when we're saying it and not saying it, and all kinds of things. And we have more than 7 people in this class. Not all of them are watching this video. Actually, some are watching on YouTube, fair enough. It takes time. So I want to give you time. All I want to do is the product rule because there's enough to do already just in that. And there's time to let me know if you have a question. It's a discussion. Yes, technically, I guess it's called a lecture, but it's more of a discussion at this stage. As I do things, if you're not liking it, I can't guess. You have to say. So we have a bunch of product rule questions. Oh, that's nice. I like it. I like it. Now, I want to build up to it, but it does say state each property. So I'd rather do fewer, at least one of them, but do it in excruciating detail at the risk of annoying you completely. What shall we do? I want to use the product rule specifically. So let's try number 4 because it's not too overwhelming. Problem 5.3, number 4. Because, and the test question may do this, because it says use the product rule, I have to use the product rule and not multiply it in, simplify it first, and then go to the derivative. It says use the product rule first, which means I have to. So 2x, x squared plus 1. Doesn't have to be complicated to practice. The principles are the same. So now I need to see multiplication with 2 things so that I can use the product rule. I have my first and my second. Product rule says, get rid of this line here. Product rule says, I'm going to do it over here so I have enough space. Derivative of the first. Now remember, maybe you didn't see the question here. It says state each property. I'm going to do this one in a lot of detail just to be sure. If you are super comfortable already, I apologize. Grab a pillow, have a nap. I'll wake you up in a second. But not everyone is at that stage. Derivative of the first times the second plus the first times the derivative of the second. That is what it says. It doesn't say anything else. That is what it says. Oh, so I have to say here, product rule. This is now a detailed one we're doing. So there, like I said yesterday, there are different versions of the question. One question is use the limit definition to find the derivative. Okay. Other question is find the derivative, but say what property you're using every step of the way. That's what we're doing now. And the last question is just find the derivative. I don't care how, I don't care what you show, just find it. Of course, that's the last one you should be doing when you're ready for it. And we'll do that for the next ones. Now, let's address this. Which one? Now let's address the first one. Actually, yes, let's do it. I can say it's 2 times the derivative of x for this one step at a time. And for the other derivative I have to do, I can say it is the derivative of x squared plus the derivative of 1, of course, brackets. Which properties have I used in that line? This is where you say stuff. And feel free, if you're watching on YouTube, you can still say stuff. There are 10 people. You don't have to be quiet. I'm looking at the YouTube chat. No one is saying a thing. You are not exempt from chatting. Constant times a function for the first one. Constant times a function. And I've used the sum property. Squeeze them in. Okay. Then I am going to, I'll just do it all. I'll just write it down and you think about what I've done. Not doing too much, but I am doing maybe a couple of steps like that. So I have done something for each of the derivatives that were there. I've done something. I've used properties. Which properties have I used? One? More than one? Which ones? Only by trying do you know where you're at. And if it's super easy for you, great. But if it's not, now's the time. Power rule for sure. Because I had powers of x, right? There was more. There was a constant property as well. I want to give these guys attention because without them, honestly, without them, I would not be able to do anything. Uh, if people don't realize their importance, well, I'm trying my best to emphasize it. They might just seem negligible because they're so straightforward, but they are crucial to all of this. And now it's a matter of simplification, which isn't too bad. I could totally do that if I wanted to. I will emphasize simplification is optional. Stop right there if you want. It is the answer. But if you feel like you want to simplify, go right ahead. But then make very sure that your simplification is correct, or just stop right there. Later on, here's my view on simplification. You've done so much of it in high school in your prerequisite courses. I don't feel it's appropriate for me to beat it to death further. It's pretty much already dead. You've done so much. You're probably sick of it. I trust that you can simplify algebraic expressions when you need to. We don't need to do it every time. When we have a need for it, like the question says something, or I have an answer I need to use further and I want to simplify it as much as possible, when I have a need, then I will simplify. I'm not going to simplify just for the sake of simplification. Okay? So you are more than welcome to stop right there with the box. But you are welcome to finish the simplification if you feel the need for it. I don't. This is just find the derivative. Whatever form, all of these are the derivative. Doesn't matter if it's as simple looking as possible. I don't care. All right. Neil. Okay. So let's see where we're at. Okay, so we have done the product rule. We've talked about the product rule. It says what it says, no more, no less. Okay. In some books, you might see these guys swapped around. I don't like that. I'd like it this way for reasons we'll see tomorrow. And if you do other math topics, vector algebra and things like that, then the order of these things are actually important. So I've memorized it like this. Whichever way you memorize it, because it's a plus, you can technically swap the terms around, whatever. Okay, so if we look at the problems, we'll see here. What if we have? Ooh, I like number 7. Number 7 looks nice. I like it. And I hope that you feel like I do, that if I look at the function in 7, I don't want to multiply those out. I don't want to simplify that first. That seems like a lot of effort. I'm pretty lazy. I want to find the derivative. And I have a property that handles multiplication. So why not just do that? But I also now see that I have 3 of them together. What do? I have 3 brackets that should be multiplied. Well, let me just set it up one step at a time. I have an x cubed minus 1. Individually, these brackets are not complicated. I have a 1 minus root x. When the time comes, I'm confident I can handle it. I have an x cubed minus x plus 1. X cubed minus x plus 1. All right. Now, again, the power rule, not the power rule. Well, yes, the power rule too. But the new one, the product rule, says what it says, no more, no less. And this is the only one I'm going to bother memorizing because it's the only one I will need. It says what to do when I have 2 things multiplied together. 2, not 3, 2. And yet my question, I have 3. What do I do? All I need to do is group 2 of them together. Come on. It doesn't really matter which 2. Let's maybe take these 2. That'll be my first function. And that'll be my second function. The product rule only works for 2. Now, my goal now is to not simplify them first, right? I know they're not big, and you definitely have a desire to FOIL it out, but sometimes I'm not going to be able to do that. Right now, we don't have a lot of variety in our functions to see why that would ever come up. I am resisting the urge to FOIL anything out. What do I do? Okay, because I don't want to rely on that. Sometimes it's not going to be possible, and I still need an option. The product rule still works as long as I see 2 things at a time. Okay, now I'm going to do this a little faster. I'm not going to write the properties. I know the question wants me to, but I need to stay awake. And maybe you don't have a pillow. You can hurt your head. I know what to do with the product rule when I'm looking at 2 things. Pink is my first, blue is my second. It's the derivative of the first that I'm not doing right now. I will think about it later. I'm setting up the product rule times the second plus the first, whatever is pink, times the derivative of the blue, second one. People tend to skip this line. So many people. And instead of seeing the derivative and preparing for what's next, they want to do this bit, for example, in one go, immediately. And they want to do when this other derivative comes up, they want to just do it. It's a risky game. Risky game. I'm not saying you can't, but know your limits. Know your limits. Get it? Limit. No? Okay. Know what you're able to do. the less you write down, the more you have to keep track in your head. And that's where things get shaky for me. But I know if I've written it out like a plan, the product rule is what I've applied. Now I'll look. What still needs to be done? Oh, this derivative? Okay. And this derivative? Okay. But having something on the paper, on the page, I can see and keep track of what needs to be done and focus on that only and not remember all the other stuff. Exactly. Know your limits and play within them. Yeah, exactly. So if you write down less, totally fine. But that requires a lot of keeping track of everything. And that's where I make mistakes. And I don't want to make a mistake. So I'm writing down this line, which really didn't take that long. Minus all the rambling, it was quite actually fast. Now I see, oh, this derivative, I'm going to make it green. It's not the best green, but I'm going to go with it. This derivative needs to be resolved. And when I look at what is inside the square brackets, it's another product, which requires the product rule, which I will now do. The derivative of the first, and again, I'm not doing it right now. I'm writing down what the product rule says, and then I'll see what's left to do. Derivative of the first times the second, plus the first times the derivative of the second. All of the green, that is green, all of that is multiple terms. It needs to be multiplied by x cubed minus x plus 1. Now I know this looks pretty bad. And you might be thinking, why didn't you just FOIL it out from the beginning? Why make it so bad? Because like I said, our functions are quite simple right now. So we have the option of FOILing it out. There are other functions we will learn, and then I don't have the option. Yet I still need to find the derivative. So I can practice that now. And of course, then I have this extra term here, right? So I'll just write it over here because I'm running out of space. Again, I'm not wasting your time with things you're never going to see. Actually, this guy didn't require much, but let's just leave it. He was already ready to go, but we needed to figure out the green one first, maybe. So now I'm over here. Now all of the derivatives are straightforward, original basic properties level. Let's see if we can do it. Stop me if you're not happy. This first derivative over here, 3x squared. And then, of course, the bracket 1 minus root x is still there, plus. The x cubed minus 1 is still there. Derivative of 1 minus root x. Now, this is where you decide, what do I need to do to handle the square root? Maybe I need to see it as x to the 1/2. I get people that just memorize the derivative of root x is 1 over 2 root x. And they are happy with that. Great. That might be you. That might not be you. Know your limits. Know how you want to do it. So regardless of which one you're at, maybe you want to write here negative 1/2 x to the negative 1/2. Maybe you want the root version. It's up to you. They are equivalent. Remember your brackets, right? Then I have a lot of stuff that just needs copying down. Same as this guy. This guy needs copying. This guy needs copying. Everyone needs copying. Well, not everyone. This last one, right? There's still a derivative here to figure out. Not hard. Basic properties. But a lot of things happened. And suddenly, when you look back, whoa, look at everything I wrote down. I'm kind of impressed. Sure, you could look at your options, and if there's an option to FOIL it out, that is an avenue you might want to go down. Not always going to be possible. Whether you believe me or not, the product rule can handle more than two things being multiplied together. It's going to get messy, yes. But if I write down enough for myself to keep track of everything, who cares how messy that answer looks? I will not be simplifying that guy, but I also don't need to. I found the derivative. It's right there. It's right there. Look at it. I'll put a box around it for you. It's there. If you want to simplify it, do it yourself. I'm not doing it. I also don't need to. Finding the derivative and simplifying algebraic expressions, those are two separate questions, in my opinion. Right now, we are practicing how to apply the derivative properties to find derivatives of functions I wouldn't even dream of using the limit definition for. And I can look at a function being made up out of pieces that are added, subtracted, multiplied. I need properties for all of them. And then, of course, you could say, oh, well, what about divide? Yes, of course I need one. That is for tomorrow. What is happening tomorrow? Tomorrow you are watching a video, pausing it, rewinding it, slowing it down, speeding it up, doing whatever you want to do. But it's sometimes nice to just watch it at your own pace, work through something at your own pace. In that video, the product rule might be repeated, so feel free to watch it again or skip it or do whatever. But I do have the issue that we have added pieces to make a function. We have multiplied pieces to make a function. Surely we can divide pieces. Think of rational functions. That's division. How do we handle the derivative of that? So I need another one for a quotient. That is your task tomorrow. And then we are nearing the end of this list. That's not the end, but we're nearing the end. With each one we add, it gets more and more complicated. Build your foundation. If you're not ready, don't go ahead if your foundation isn't solid. You're building on it. If it's shaky, it's going to fall apart. It happens every single semester I see it. Regardless of my best advice, there's always someone that ignores it, and I don't want that to be you. I don't want that to be you. Build on a solid foundation, and you're giving yourself the best chance for success. And I guarantee you, if all the effort you put in now, the last month, November, is going to be smooth sailing if you've put in the effort now, or it'll be a disaster if you didn't. That's up to you which way you want to go. Up to you. I can only give you advice. Any general questions up to this point? Lots of problems to practice. Any thoughts? Anyone not sure what they're doing tomorrow? No? All right then. Well, someone's typing. It's exciting. Someone's going to say something. What could it be? I don't know. Ooh, more people are typing. I'm on the edge of my seat. Someone's going to make contact. Where can we find more basic questions? If you look on the website, there are suggested. Oh, why am I opening that? There are suggested exercises from the official textbook. There should be many there. Let's have a look. I need to open the website. Hold on. Opening the website. let's see here. Where are the list of exercises? Obviously not something I open all the time, right? Let me see here. Well, under additional exercises, I guess that would be fitting. Oops. Exercises that will be used in class. That's the problem book. Blah, 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 blah. A list of additional textbook exercises can be found here. Oh, okay. So we are where? There we go. We are at differentiation rules, topic 5. So there are uh, section 2.4, number 1 to 14, 2.6, number 1 to 14, that you can look at. Depending on the wording of the question, whatever, but you can use more functions. Literally every book has, every calculus book has derivative questions. You just want to look at the first ones before it gets too fancy. Other question, is this going to be on the first midterm? When is the first midterm? That is a very good question. Wow. I should probably know these things, huh? Let's see where we at. We're in October. Okay, yes. So the midterm's coming, I guess. If you don't, oh wow, if you don't attend a Q&A session, then I guess we might not be speaking again until the midterm. But we have multiple catch-up sessions. See, you're watching the video tomorrow. Hopefully this is big enough. Zoom in more. You're watching the video tomorrow. That's the yellow block. Then we have a catch-up open class session where you could just discuss whatever you want. Nothing new. Friday. Then we have another one because after Thanksgiving, we might need a catch-up and in preparation for our midterm. So we're going to have lots of time. Bring your questions, bring your questions, bring your questions. The midterm 1 will go up to topic 3. Topic 3. It'll go up to rates of change, up to instantaneous rate of change. So in our problem book, actually, it's over here. Topic 1 on my list, it's like prerequisite pre-calculus stuff. Most of it review. Then topic 2 is limits, and topic 3 is rates of change, average rate of change, instantaneous rate of change, which technically I know instantaneous rate of change is the same as the derivative, but technically at that stage you don't know that, so there's no mention of a derivative there, but it is the same as the limit definition. So we are stopping. It's topic 1, 2, and 3. Topic 1, 2, and 3. That should be on the website too, isn't it? Oh, look at that. Test. Topics 1 to 3. There you go. So everything is on the website as well. So yes, we do get a little bit ahead of ourselves because I want to give people time to study for a midterm. Even though not everything we're doing right now is on this coming midterm, there's a little bit of a delayed effect, unfortunately, but that's common. All right, let me know if you have any other questions. We've got lots of catch-up sessions. Tomorrow's a video, and then it's all catch-up, all preparation for the midterm. Until then.